All right, here's part 2 of the matter and atoms videos. So we already talked about we already talked about matter, right? Anything that has mass and takes up space. We can divide it into two simple categories: mixtures and substances. A mixture is multiple substances. A substance is only one kind of thing. And then I can we looked at the physical and chemical properties of different kinds of things. All matter has physical and chemical properties. And I know that matter is made of elements, and those elements are tracked in the periodic table. We're going to take a closer look now into things called molecules and compounds. So think of the wax on a candle here. If you cut a piece of wax, is it still wax? If you cut that smaller piece again, is it still wax? At what point does it stop being wax? And the answer is when I get it so small that I'm cutting these molecules in half. Wax is made of long molecules made of carbon and hydrogen that we call paraffin. And if I could cut one of these atoms in half, or well, I'm sorry, one of these molecules in half, then that would no longer be wax. But until I can cut that small, it's wax. A molecule is a group of atoms that are chemically bonded together. For instance, up here I have two kinds of molecules. I have O2, which is made from two atoms of oxygen, and I've got H2, which is made of two atoms of hydrogen. So this is one hydrogen molecule, this is one oxygen molecule. And right now it's a mixture because I have two different kinds of things in here. If I took those magic tweezers, I would pull out a molecule, and who knows what it would be. Could be oxygen, could be hydrogen, I don't know. So that means it's a mixture. A compound is when I take more than one kind of element and put them together to form something new. These two sides of this picture, my mixture of O2 and H2, and this water over here, these H2O molecules, have the same amount of matter. There are 4 oxygens and 8 hydrogens on each side. I have just created a compound now instead of these single substances. So a compound, just like a compound word is when you jam multiple words together, parking lot or nighttime, I'm taking two words and joining them together. A compound is when I take two elements and join them together into one molecule. What do you suppose these 4 things have in common? Candle wax, non-toxic, soft, melts easily. Aspirin, a hard, crunchy tablet with the ability to make me feel less pain. Plastic wrap, somewhat stretchy, see-through. And gasoline, a very explosive liquid. All 4 of these things are made of just 3 kinds of atoms: carbon, oxygen, and hydrogen. I like to relate the periodic table to the alphabet. With 26 letters in the English alphabet, I can make more than 200,000 words. Well, there's 92 naturally occurring elements. With 92 elements, I can make trillions of substances. And we label them all with a chemical formula. You've probably heard of H2O. It's the most popular, most famous chemical formula there is. But every kind of substance has its own chemical formula. So breaking this apart is a lot easier than you probably imagine. The H is my element symbol, and if I check my periodic table, I find out that H stands for hydrogen. And the 2 in this subscript means that there's 2 hydrogen atoms in each molecule. 1 and 2. I'm a stickler for this one too. Notice that the 2 is submerged. It's subscript. It's down below the line. But it's not all the way below the line. And it's not just a little 2, half size, written in line next to the H. Everyone has a different way that they like to write these, and most of them are wrong. The only right way to write a chemical formula is with the middle of the 2 in line with the bottom of the H. If I was writing this on lined paper, the 2 would be below the line on the paper. It's not good enough to just write a little tiny 2 next to the H. It needs to be submerged. The O indicates oxygen, and there's no subscript here. So I know there's only one oxygen in the molecule. H2O is a pretty simple one. There's a lot harder ones out there, like sodium bicarbonate or baking soda, NaHCO3. This means that this molecule has 3 oxygen atoms, right? And 1 carbon, 1 hydrogen, and 1 sodium. Notice the capital N, lowercase a. That lowercase a belongs to the N. It's part of the same symbol. As I said in the first video, I've had a lot of students tell me that this was 3 atoms of cobalt because they didn't acknowledge that this is a capital O. They looked at it and saw CO. They found CO on the periodic table, and they said that's cobalt. And that's not what this is. This is a carbon and 3 oxygen. So pay attention to the state of the letter. Is it capital or is it lowercase? It's very important. And where is that number located? So the properties of a compound actually depend more on the exact structure of the molecule than they do on what elements it's made from. For instance, this is aspirin, C9H8O4. It's made out of carbon, hydrogen, and oxygen. Notice it has this wheel shape. That's a very common shape in large molecules made of carbon. It also has a little branch up top and a larger branch off to the left. But just like I can jumble letters and get different meanings, right? These same letters, I could write funeral or real fun. It depends on how I put them, right? The arrangement of the atoms depends too. These 3 compounds are very different, but they all have the same chemical formula, C9H8O4. The difference is the shape. Here's my aspirin with its 2 limbs. This methyl ester has a large, long limb coming off of one spoke, whereas this peroxide has one. This isn't even a branch. This is like a whole other side of the molecule, and 1 branch coming off the bottom. So the shape of the molecule makes a huge difference in its properties. So when we write these on a piece of paper or we try to represent them, they're too small to see. So the only thing we can do is create a model of them. There's a lot of different ways to represent the same thing. These are all heads, but they all serve different purposes. Smiley face is just there to make you laugh. Where the model on the right here might be used to tell you about the organs inside the head. This might be a prop in a play or just, something to study to look at the bones in the head. I can't see where the bones in the head are very well from here. Maybe I'll just put this up as an artwork piece. So there's many ways to represent the same thing. Same thing's true of molecules. This is the chemical formula for acetic acid, the active ingredient in vinegar, the thing that tastes so sour in vinegar, is CH3COOH. And the most common way you'll see it shown is with this structural diagram here. We use an element symbol as a marker for the atoms, and then show lines to show bonds. So here there's a double bond between carbon and oxygen, and single bonds between everything else. You can also do the ball and stick model. These are pretty popular. If you've ever used a marble kit in school in order to build a compound, this is a representation of that. A circle for each atom and a little stick to show me where the bonds are. You might see the space filling model, which just shows me the size of the individual atoms, or a molecular surface one, which is a ball and stick, but also shows me the outside edge of the electron clouds. In general, in class, we'll use some sort of a ball and stick model, or this kind of model here, this structural diagram. Not all substances are molecules, though. Aspirin is a molecule. If I reach into aspirin with my magic tweezers and pull out a molecule, I'm going to get the same thing every time. But a lot of things, anything that involves a metal, is an ionic compound. So sodium is a metal. And when you mix it with chlorine, it shares electrons rather than bonding with each other. And so sodium is attracted to chlorine, and chlorine is attracted to sodium. And so what happens is that each atom gets bound to all the atoms around it. So instead of being one carbon linked to one carbon linked to one carbon linked to a hydrogen, I get a chlorine atom bound on all sides to a sodium. And they make these large matrices. So if you've ever looked at a salt crystal, it's always a cube. And that's because salt at the molecular level is a cube. And as I build more, if I put more and more atoms into it, it becomes bigger and bigger and bigger cube. If you've ever seen like a geode, is like a cool rock that's broken open and it's got lots of crystals inside of it, and those crystals have shapes of like diamonds and weird angles and things. If you were to zoom down to the very basic level, you'd see that the atoms are constructed in that fashion. The size of the atoms and the charges they have and the different mix of atoms that are in that compound will change the shape of the crystal. So salt is not a molecule. It's an ionic compound. The thing about ionic compounds is that if I put them in water, they tend to dissolve, and they can these bonds create ions in the solution. So an ionic compound is a compound such as a salt in which positive and negative ions attract each other to keep the matter together. An ion is an atom or small molecule with an overall positive or negative charge. We're going to get into ions a little bit later. For now, just know that they exist, and they have a little bit of a charge, like a magnet, positive or negative, and opposite charges are going to attract. That's all we need to know about atoms, molecules, and elements for now. We'll dive into these topics in a little bit more depth, but you'll really explore them when you take chemistry. I think that's 10th or 11th grade. So thanks for watching, and I will next do a video on the assignment in class.